Hi everyone and welcome back to the iMachinesTV channel. Sheet pile driving is a crucial process in bridge construction that involves the installation of interlocking steel sheets, known as sheet piles, into the ground to form a continuous barrier. These sheet piles are commonly made of steel due to its durability, strength, and resistance to corrosion. The primary purpose of sheet pile driving in bridge construction is to provide temporary or permanent support to excavations, retaining walls, and foundation structures. Sheet piles are installed vertically or at a slight inclination into the ground using specialized equipment such as vibratory hammers, impact hammers, or hydraulic presses. The chosen method depends on various factors such as soil conditions, environmental constraints, and project requirements. The driving process involves carefully positioning the sheet piles at predetermined intervals along the bridge's alignment. The sheets are then driven into the ground using the selected hammer or press, which transmits a powerful force to the top of the sheet pile. This force drives the sheet pile into the soil, allowing it to penetrate and create a stable foundation. Sheet pile driving requires skilled operators and careful planning to ensure proper alignment, adequate penetration depth, and interlock between adjacent sheet piles. Engineers consider soil conditions, groundwater levels, and the anticipated loads to determine the appropriate sheet pile length and design. The process may involve pre-drilling to facilitate driving in dense or hard soil layers. During sheet pile driving, vibrations and noise are inevitable. To minimize the impact on the surrounding environment, noise barriers, vibration monitoring systems, and appropriate mitigation measures are employed. Environmental regulations and community concerns often dictate the implementation of noise and vibration control measures. Board piling is a widely used construction method for creating deep foundation systems that provide support and stability to structures. It involves the use of specialized equipment and techniques to install piles, which are long cylindrical columns made of reinforced concrete. This article will discuss the various steps involved in the board piling method, from stakeout and referencing to the area cleaning process. The first step in the board piling method is the stakeout and referencing of the proposed pile location. This involves marking the exact positions where the piles will be installed according to the construction drawings and specifications. Accurate stakeout ensures that the piles are placed in the correct locations and are aligned with the intended structural design. Once the stakeout is complete, the next step is pre-boring using a drilling bucket. A hydraulic drilling machine is typically used for this purpose. The drilling bucket is attached to the drilling machine and is lowered into the ground at the designated pile location. The bucket is then rotated and drilled into the soil, creating a hole of the required diameter and depth. To maintain the stability of the borehole during the drilling process, a temporary casing is driven into the ground by gravity. The casing, usually made of steel, helps prevent the collapse of the borehole walls and maintains the integrity of the hole. The casing is driven into the ground until it reaches a stable soil layer or the design depth. Once the temporary casing is in place, drilling continues below the casing. A polymer-based slurry is commonly used during this stage to stabilize the borehole and facilitate the drilling process. The slurry, which is a mixture of water and a polymer additive, helps to prevent the collapse of the hole and provides lubrication for the drilling equipment. The installation of rebar cages is a critical aspect of the board piling method, ensuring the structural integrity and load-bearing capacity of the piles. In this method, it is common to use 3 rebar cages per one pipe to provide enhanced reinforcement. The rebar cages, which are prefabricated structures, consist of steel reinforcement bars arranged in a specific configuration. These rebars are designed to distribute the load evenly and withstand bending, shear, and axial forces. By reinforcing the pile, they enhance its strength, durability, and resistance to external forces. During the installation process, the rebar cages are carefully positioned within the borehole after the drilling and temporary casing stages. The first cage, known as the starter cage, is placed at the base of the borehole to serve as the foundation for the subsequent cages. After the starter cage is in place, the remaining cages are sequentially lowered into the borehole. Each cage is aligned and connected to the previous one to create a continuous reinforcement system. The cages are designed with interlocking features or connecting splices to facilitate the connection and maintain the integrity of the reinforcement. During the installation, it is important to ensure the vertical alignment and spacing of the rebars within the cages. Proper alignment guarantees that the rebars are positioned correctly to effectively resist the applied loads. In some cases, additional elements such as stirrups or spirals may be incorporated into the rebar cages. Stirrups are typically used to resist shear forces and prevent diagonal cracking, while spirals enhance the ductility and resistance to torsional forces. Following the installation of the rebar cages, a tremie pipe is inserted into the borehole. The tremie pipe is a long, narrow pipe with a funnel-shaped hopper at the top. It is used to place the fresh concrete into the borehole. The pipe is lowered into the borehole until it reaches the bottom, and the concrete is poured into the hopper. As the concrete flows through the pipe, it displaces the slurry and fills the borehole from the bottom up. This ensures that no voids or air pockets are formed in the concrete and that it is properly compacted. During the concrete placement process, several tests are conducted to ensure the quality of the concrete. One such test is the slump test, which measures the consistency and workability of the fresh concrete. The slump test involves filling a standard slump cone with concrete, compacting it, and then removing the cone. The difference in height between the top of the cone and the height of the concrete slump is measured to determine the slump value. The slump value helps assess the flow properties of the concrete and ensure that it meets the required specifications. In addition to the slump test, sounding is performed to check the integrity of the concrete. Sounding involves tapping the sides of the pile with a hammer and listening for any hollow or void sounds. A solid, dense sound indicates that the concrete has properly filled the borehole without any significant defects or voids. Once the concrete has been placed and tested, the tremie pipe is slowly lifted out of the borehole. This process allows the concrete to settle and prevents any disturbance or segregation of the concrete. The tremie pipe is carefully removed, ensuring that no excess concrete is left behind. After the removal of the tremie pipe, the temporary casing is gradually extracted from the ground. This process is carried out slowly to minimize any disturbance to the surrounding soil and to maintain the stability of the pile. The extracted casing is typically cleaned and reused for future piling works. Finally, the area around the completed pile is thoroughly cleaned. Any excess concrete, slurry, or debris is removed to ensure a clean and safe working environment. This step is important to maintain the integrity of the construction site and to prevent any potential hazards or obstructions. Pile head cutting is a crucial process in construction and civil engineering projects. It involves the removal of the top portion of a pile after it has been driven into the ground. The pile head cutting process is necessary for various reasons, including adjusting the pile length to the required height, facilitating further construction or retrofitting, or preparing the pile for load testing. To carry out pile head cutting, construction workers often utilize a hydraulic jack assembly system. This system is designed to provide the necessary force and precision to cut the pile head effectively and safely. Let's delve into how the hydraulic jack assembly system works and its components. The hydraulic jack assembly system typically consists of several components, including a hydraulic jack, a cutting tool, a support frame, and a power source. The hydraulic jack is the central component of the system, responsible for generating the force required to cut through the pile head. It operates using hydraulic pressure, which is created by a power source such as an electric motor or a diesel engine. The process of pile head cutting using a hydraulic jack assembly system begins with the workers measuring the desired length of the pile to be cut. This measurement ensures that the pile will be adjusted to the required height or be prepared for further construction activities. Once the length is determined, the workers mark the position on the pile where the cut will be made. Next, a concrete cutter is employed to create a circular cut around the marked position. This circular cut defines the area from which the pile head will be removed. The concrete cutter is carefully guided along the marked line to ensure an accurate and clean cut. After the circular cut is complete, the hydraulic jack assembly system comes into play. The support frame is positioned securely around the pile, providing stability during the cutting process. The hydraulic jack is then connected to the cutting too. As the hydraulic jack applies pressure, the cutting tool starts to penetrate the concrete and steel of the pile head. The hydraulic pressure provides the necessary force to break through the material, allowing the cutting tool to progress steadily. The cutting process continues until the entire pile head is separated from the remaining pile. Once the pile head is fully cut, it can be removed using appropriate lifting equipment. The hydraulic jack assembly system may also include additional features to facilitate the removal of the concrete end. These features could include gripping mechanisms or attachments that can be affixed to the end of the pipe to pull out the concrete section efficiently. The construction of prefabricated reinforcing bars for bridge piers involves a systematic process to ensure their proper installation and structural integrity. At the construction yard, the prefabricated reinforcing bars are assembled according to the project specifications. These bars are designed to provide strength and support to the bridge piers, which are critical components of a bridge's superstructure. To lift and install the prefabricated reinforcing bars, a rough terrain crane with a lifting capacity of 80 tons is utilized. The crane is capable of handling heavy loads and maneuvering on challenging terrains, making it suitable for this construction task. The crane is carefully positioned near the specified installation area, ensuring stability and safety during the lifting process. When suspending the prefabricated reinforcing bars, several factors are taken into consideration to guarantee their proper alignment and structural performance. These factors include the potential deformation and yielding of the rebars, as well as the misalignment of the rebar arrangement. To address these concerns, rebar reinforcements made of equal angle steel measuring 65 by 65 are utilized. The rebar reinforcements are strategically placed and fixed to the main rebars in the vertical direction using fixing metal fittings. This additional layer of reinforcement helps enhance the overall strength and stability of the bridge piers. The suspension fulcrum, which serves as the point of support during the lifting process, is positioned on the rebar reinforcements. This ensures that the load acting on the suspension fulcrum is distributed evenly, minimizing any potential stress concentration points. To further optimize the lifting operation and ensure proper placement of the prefabricated reinforcing bars, a chain block is employed. The chain block is connected to a suspension support material, typically made of H-steel, which allows for height adjustment during the lifting process. This height adjustment mechanism enables precise positioning of the prefabricated reinforcing bars at their designated location. With the chain block, the prefabricated reinforcing bars are carefully lifted and maneuvered into place at the predetermined position. The lifting process requires skill and coordination from the construction crew to ensure the safe and accurate installation of the bars. The crane operator, riggers, and other team members work together to monitor the lifting operation and make necessary adjustments as required. Once the prefabricated reinforcing bars are in their final position, they are securely fixed and connected to the existing structural elements. This is typically done using welding techniques or mechanical fasteners, ensuring a strong and durable connection. The installation process is meticulously executed, adhering to industry standards and project specifications to guarantee the structural integrity and safety of the bridge piers. The installation of box girders on the Tangerang Merak toll road, undertaken by the Wagner Indonesian Bureau, stands as a remarkable example of engineering prowess and innovative thinking. This project successfully executed the installation process without disrupting the flow of traffic, showcasing Indonesia's expertise and advancements in the construction industry. Box girders are critical components in the construction of elevated highways and bridges, providing structural support and stability. Traditionally, installing box girders necessitates the closure of sections of the road or the redirection of traffic, resulting in inconvenience and delays for commuters. However, the Wagner Indonesian Bureau devised a brilliant strategy to minimize these disruptions. Firstly, meticulous planning played a crucial role in ensuring the seamless execution of the project. Extensive surveys and studies were conducted to assess traffic patterns and determine optimal timeframes for installation. By analyzing peak traffic hours and identifying periods of lower traffic volume, the team was able to pinpoint suitable time slots for the installation process. Another key factor in the success of this project was the implementation of an innovative construction technique known as the incremental launching method. This method involves constructing the bridge segments adjacent to the main span and then gradually sliding them into place. By doing so, the need for temporary road closures was significantly reduced. To accomplish this, the Wagner Indonesian Bureau utilized specialized equipment, including hydraulic jacks and launching trusses. These tools allowed them to precisely control the movement of the box girders and ensure a smooth and accurate installation process. The careful coordination and synchronization of these operations minimized disruptions to traffic flow. Mobile cranes play a crucial role in the erection of 50-meter rob plate girders during bridge construction projects in India. These cranes are indispensable in handling heavy loads and providing the necessary lifting capabilities to ensure the safe and efficient installation of these massive steel structures. When it comes to erecting large bridge girders like the 50-meter rob plate girder, mobile cranes offer the flexibility and mobility required for the job. They can be easily transported to the construction site and set up in the desired location. Mobile cranes come in various sizes and configurations, allowing for customization based on the specific requirements of the project. The installation process of 50-meter rob plate girders involves multiple steps, and mobile cranes play a pivotal role at each stage. Firstly, these cranes are used to unload the prefabricated girders from transportation vehicles, such as trailers or flatbed trucks. Due to their high lifting capacity, mobile cranes can handle the weight of the girders and position them precisely for further installation. Next, mobile cranes are employed to lift the girders and position them accurately in their designated places. This requires precise coordination and skilled operators who can maneuver the crane with precision to ensure proper alignment and fit. The ability to rotate and extend the crane's boom allows for flexibility in reaching different areas of the construction site. Once the girders are in place, mobile cranes assist in securing them by connecting various components, such as bolts, plates, and welds. These cranes offer stability and control during this crucial process, ensuring that the girders are securely fastened to withstand the loads they will bear once the bridge is completed. Mobile cranes also play a vital role in the final stages of the installation. They are used to lift and position auxiliary equipment, such as formwork and scaffolding, which are necessary for subsequent construction activities. The versatility of mobile cranes allows them to handle different types of equipment, making them essential for the overall bridge construction process. Safety is of paramount importance during the erection of 50-meter rob plate girders, and mobile cranes are equipped with advanced safety features to ensure the well-being of the workers and the integrity of the structure. These features include load monitoring systems, outriggers for stability, and operator training to adhere to proper safety protocols.